The land of mathematics is an exotic and puzzling place. A strange language is spoken there, with talk of homeomorphisms, differentiable manifolds, and transfinite numbers. But also to be found there are magnificent landscapes, spellbinding ideas, and occasionally, even useful things. So let's take a whirlwind tour of the land of math. You just need a guide, that's me, and a functioning brain, that's you. We're not really going to do any math, just take a look at the countryside. What is a number? How can it be named, recognized, described? The question may seem rather basic. We thought we sorted that out when we memorized the multiplication tables. But what if this reassuring familiarity was hiding a landscape very different from that of our classroom memories? The region of mathematics concerned with numbers and their properties is much more vast than we would imagine. And rather than a uniform plane stretching out into the distance, we need to imagine a mountainous region with inaccessible summits, cliffs, and still unexplored valleys. Let's go and take a look. We'll start off gently with the oldest and most familiar numbers, the so-called natural numbers, used for counting the heads of cattle or dinner guests. We can represent natural numbers as notches in a stick or peaks in an infinite mountain chain. Or we can put them together in a set that we call capital N. Natural numbers are solid, reliable, and no bother. As long as we stick to adding or multiplying them, the results remain within the capital N set, which is practical. As for subtraction, that requires us adding negative numbers. So we find ourselves in the capital Z set, that of integers, but the landscape remains pretty much the same. Whole numbers are so beautiful, so perfect, that in the 6th century before our era, a number religion was born. For Pythagoras and his disciples, the number, whole of course, was the principle of all things. Of course, division complicates the picture because the result often falls outside of the N set. To describe 1/3 of 2, or half of 5, we have to use a new notation, fractions or decimals. So we arrive in a landscape which is more vast, the Q set, containing numbers which we call rational. The Q set is very different from the N set. N is discrete, meaning that if we zoom in on a point chosen randomly, we will quickly find a deserted area. Q, on the other hand, is dense. At whatever point you zoom in, and to whatever degree of magnitude, you always have an infinite quantity of rational numbers in your field of vision. Although rational numbers may be less presentable than their integer cousins, they're still part of the family. They express the relationship which exists between two integers. But here's an unexpected guest to spoil the party, wreak havoc in this well-ordered universe, and throw the Pythagoreans into confusion. And all because of Pythagoras' theorem. Indeed, remember, Pythagoras' theorem states that for a right-angled triangle, the square on the hypotenuse is equal to the sum of the squares on the other two sides. In certain cases, the length of the hypotenuse will be an integer, but in other cases, it's more complicated. For example, let's try with an isosceles right triangle, the length of the sides of which is 1. What is the length L of its hypotenuse? Pythagoras' theorem tells us that L squared equals 1 squared plus 1 squared, meaning that L equals the square root of 2. The drama came when the disciples of Pythagoras discovered and proved that the square root of 2 cannot be written as a fraction. The diagonal of this square is a monster. It exists, and yet no number is the measure of it. It defies ratio, meaning both calculation and reason. It is irrational. The whole vision of the Pythagorean world finds itself in question. Legend has it that the person who revealed the existence of this catastrophe was thrown into the sea by their fellow students. As the historian Proclus put it, the unexpressible, the shapeless, must be kept absolutely secret. Those who have divulged it must be eternally buffeted by the waves. It was on the other side of the Mediterranean, during the medieval period, that the story continued. Arab mathematicians, and notably Abu Kamil in the 9th century, realized that these monsters were necessary for resolving second and higher degree equations, and that they therefore needed to be considered as mathematical objects in their own right. As of the 17th century, notation by fractions was gradually supplanted by decimal notation, which allowed fractions and roots to be written differently. The square root of 2 can therefore be written, but only in part. Because unlike rational numbers, the decimal part of which always ends up in a repetitive loop, that of an irrational number is an endless row of figures in which no order seems to appear. Furthermore, that's how it can be recognized. A number is an irrational if and only if its decimal representation is non-terminating and non-repeating. In the 17th century, the status of these numbers, which were then referred to as deaf numbers, was controversial. Isaac Newton considered them to be numbers, while Blaise Pascal, and later on Diderot and D'Alembert's Encyclopedia, refused them the status. Newton finally won the day. In the 19th century, the notion of real numbers came into being. This meant that rationals and irrationals were put into the same set, that of the reals R, which became the ordinary landscape of algebra. It was also at this time that the idea of an equivalence between real numbers and the points on a line came about, and that Georg Cantor proved that the irrationals are infinitely more numerous than the rationals. Consequently, if we randomly choose a point on a line, the probability of landing on a rational number is simply nil. All the numbers which we use in real life are just the tiny tip of the colossal iceberg of irrational numbers. Let's take a closer look at this iceberg. Amongst the irrationals, all are not equal. Those we come across most frequently in real life are those which are solutions of algebraic equations. The square root of 2, for example, is a solution of x squared minus 2 equals 0. This other number here is a solution of 7x cubed minus 18 equals 0. And this one is a solution of 19x cubed minus 7x squared minus 5x plus 3 equals 0. These algebraic numbers are the most accessible of the irrationals. They have their own set, sometimes designated by the symbol q overline. But outside this set, in the most secluded regions of the real set, live numbers which are the solution to no algebraic equation. These are known as transcendental numbers. Some of them play an important role in mathematics. That's the case with e, the constant at the base of natural logarithms, and above all, the uncontested star of transcendental numbers, the famous pi. We know of approximations of pi dating back to the 17th century before our era. And yet, it was in 1761 that it was proven to be irrational, and in 1882 that it was proven to be transcendental. But pi is a tree which hides a forest of transcendental numbers. If we return to the line of reals and we choose a point at random, the probability of landing on a number which is not transcendental is once again nil. The vast majority of numbers are irrational and transcendental. Apart from a few exceptions like pi and e, they can only be described by listing the infinite string of their decimals. You might as well say that they're completely out of our reach. So this is where we come to the end of our hike, in an infinite and obscure cave where almost the totality of numbers are floating, unknown and forever unknowable. Well, let's say almost the end of our hike, because even the most secluded caves are sometimes visited by an audacious speleologist. In 1933, David Champernowne, an English mathematician, invented a strange number. You obtain it by sticking end-to-end the infinite succession of natural numbers. This strange number is irrational and transcendental, but it's also what the mathematician Jean-Paul Delahaye called a universe number. It contains all the sequences of finite digits possible, all the possible sequences, all the numbers which are not infinite are included in the Champernowne sequence. And because since the invention of CDs and DVDs, we know that all information can be transposed into a sequence of numbers, a universe number contains all the books written, or to be written, as well as all the films, all the images, and all the songs in the universe. Apart from certain particular cases, it's very difficult to determine if a given number is a universe number. We think that pi and e are, but no one has yet been able to prove it. However, what we know since 1909 is that almost all real numbers are universe numbers. So if we randomly put our finger on the line of reals, the probability of falling on anything other than a universe number is once again nil. In brief, the numbers we encounter at primary school only represent a tiny fringe, drifting in the ocean of universe numbers, for which, fortunately, there exists no multiplication table.